Okay, hello everybody. I hope you've had a restful break, or I hope that you've taken some time to rest. There's kind of a temptation or pressure when you're in graduate school to be working all the time and take someone who's been there. It's really easy to burn out, and that time of rest is super important, even if the only thing you care about is productivity. So I hope you took some time. If you didn't, well, I guess there's only spring break. It's nice to see you all again. This is going to be a direct extension of the course from last semester. We're going to be picking up where we left off. So a lot of the structural things that I'll talk about today ought to be kind of familiar. I'm going to reiterate some things that you may have heard before, because I think it's important that you know all the philosophy that went into designing the course and why we made certain decisions when doing the course or when constructing the course. I'll also go through a brief, very high-level overview of the content from last semester. It's not going to be comprehensive. But you know, I hope at least it serves as a refresher of the kinds of things that we talked about last semester. By the way, also this semester, Bill is not co-teaching the course. He told me that he's going to be sitting in. One of the reasons we want to co-teach in the first place was if one of us is not teaching the course, we want some continuity in the content. So I'm still hoping we can maintain that. So you might see him sitting around, although he's not listed as an official instructor anymore. Austin is still going to be handling the drills though. So just like last semester, we've got lectures and drills. Something that's new to try to carry on something that we started last semester is that the lectures are all going to be live streamed. And I think the drills might be too. I'll double check with Austin on that. So we're getting all fancy. But the idea, of course, is to have those present as extra resources if you want to review a lecture or a certain part of a lecture. Whatever. I hope that you find them useful. I have no idea how many people used them last semester, although I did have a few people tell me that they did consult them. So they're there if you want them. Of course, the lectures are intended to be more conceptually focused, although I do go through some of our content in the lectures as well. The drills are intended to be applied. I really hope that this semester we can structure in a few more like exercises where Austin is there for guidance if needed before you're working independently. I've found in the past that those are a really great time to like try out things without trying to keep up with Austin, whoever's teaching, at that kind of frantic pace. So I'm hoping we get there, although we don't have any more time for drill than we did last semester. So we'll see how that goes. I think everybody's filled out the scheduling thing for the drill, is that right? If you haven't, consult your schedule, fill it out. We got into a scheduling snafu. I thought we had that all cleared up last semester, but apparently not. So I'm going to try to get that back to you as soon as possible. I mean, it's pretty important that that's on the calendar. So stay posted. You'll get an email from either Austin or me with more details. We'll see as we can do it. And of course, we've got readings and homeworks to reinforce the concepts. Something that's a little bit new this semester is that your syllabus does not have the full list of readings, because I put on the syllabus last semester that I'm going to be changing the schedule, switching up some of the readings as necessary. But I think the fact that it wasn't on the syllabus at all actually led to some confusion, because a couple of people were like, well, why is the schedule changing, or why are the readings changing? Well, the place where you can find the most up-to-date information is on the course website, which I'm going to try to keep more up-to-date than it was at some points last semester. I think there were a couple places at times when there was some confusion about who was posting what. Anyway, point being, that's where to go for information. Something else that I'm going to do this semester is be a bit more diligent about saying before we go into a lecture what readings are covering this particular section of the material. So just to forecast, the readings for this unit are already up on the blackboard. I think the first reading that we have up there is Judd chapter 8. If you want to get a head start, you can go ahead and start reading that. There are 3 readings that I've chosen. I'm still thinking about whether to put some supplemental readings up there, but those are the ones that at bare minimum I want you to cover. And we have the same testing schedule as before, 2 in-class exams, 3 take-home exams. The in-class exams are generally a bit more conceptually focused. The take-home exams are generally a little more applied. And just as before, you'll get keys to everything. There's some expectation that you're looking at the key to check yourself, although for the exams at least, I'll get feedback to you. So if I had more person power, I'd give you feedback on the homeworks as well, but that would be a lot of work. And as was true last semester, it's really important to me that I'm adjusting the course in response to what's working and what's not. And the only way I could do that is getting feedback. So there's 2 scheduled, basically course evaluation surveys, whatever, that I'm going to have you or ask you to do, not require, so that I can basically check out to see how things are going. And the course evaluation is going to serve one more purpose that I'll get back to in a little bit, but this is an important part of the class. Yeah.
On here, for the take-home exams, it says I think the dates are when they're due are from last semester, so can we just assume they're due the following Wednesday after they're assigned?
Oh, yes, that's when you'll receive them.
Okay. Or when they're due?
So what's on the syllabus is when they'll be assigned, and then they'll be due the following week.
Okay.
Sorry. This won't come as a surprise to any of you, but this course is hard, and it's structured that way. So I know that there was some adjustment period last semester. Hopefully that adjustments need to be an adjustment. Hopefully it's less shocking. But I've made the workload somewhat high. The tests are intended to be difficult, but hopefully not unfair. So yeah, setting that expectation out there. Research is hard. There's a lot to cover. There's a lot of topics that we'll be going through, and the topics sometimes are conceptually difficult. So I don't know for sure, but I would expect that this would be one of the harder courses that you'll take during your graduate career. I don't know if that's true, but there's certainly a lot to cover. There's a lot of content, and I'm asking a lot of you, and I know that. So my hope is that, even if I'm challenging you a bit, I'm also giving you the tools and resources needed to rise to that expectation. If that's not working, I'm open to making adjustments, and I tried to do that last semester. But yeah, the course is intended to be hard, and I know that. But I hope it's useful and that you get something from it. As with last semester, we're going to be continuing on with R&R Studio. Y'all should have that installed. Not sure if I put the installation instructions up on the Blackboard site, but I'll put them up there. But I think all of you should have them by now. Something that I know I said this a couple times last semester, but I just want to reiterate because I've had a couple people come up to me and say hey, my lab uses SPSS or other courses use SPSS or some other software. I'm not sure I want to continue on with R, or I've had that conversation with a couple people. So let me say up front, if you're getting direct pressure from your lab supervisor to use whatever data analysis software is available, there's only so many things that you can do. I'm hoping that you'll still be able to communicate with someone about data analysis by focusing on the results and less on code. But I'm I realize that different labs have different practices, and it can be hard to fight against those if you want to do something different. But what I will say is that I chose to teach this class in R, not because it was easy. I mean, actually, it's kind of the opposite, at least up front. But because I'm hoping that I'm making an investment in you. So the reason that we chose R is that I think, and I have some evidence, that there might be some longer term benefits for you. So one of those benefits is that knowing R is an employment skill, as is knowing how to do some amount of programming. This isn't a programming class, but you're learning some programming concepts as part of doing the class. So I'll give you some evidence for this. There's a blog post, or this might be like an online paper, but you can check the source if you want. But these are job postings for data science jobs, data science, I mean, basically it's data analysis. And this is just showing the number of postings on this jobs website that involve different kinds of data analysis software. So up there is R, down here is SPSS. So at this moment, I think this was in 2015, there were about 3 times the number of postings that involved R as involved SPSS on this one particular job website. If you're thinking about alternatives, well, and you're focused on academia, let's say that you want an academic job, which is fine if that's what you want to do. But even if you're focused on academia, SPSS is in decline. So this is from that same posting. This red line is SPSS. Once upon a time, it was very dominant, but that is not so much the case anymore. And this is a trend that's only continued throughout the years. There are lots of reasons for this. R is open source, R involves programming, and more people are starting to understand that programming is something that is pretty powerful and can do a lot. It's also extensible, yada, yada, yada. The main point that I want to make here is that even if you're focusing on academics, this is an ongoing trend, and I want to look towards the future and give you a skill that will be useful to you in the future and not just now. The other major set of reasons is that R is growing a lot, very rapidly. So this is from another blog post. Stack Overflow is a network of Q&A websites. They're very useful. I use them a lot. There's one called Cross-Validated for Statistics that, if you have a very specific question, can be very useful for getting some resources or even getting a full solution. So just a plug for Stack Overflow. This is a graph of the types of questions on Stack Overflow involving different kinds of programming languages. And this blue line right here is the number of questions involving R. A pretty dramatic upward trajectory, indicating or perhaps suggesting some of its growth. If you want to know who's visiting the R questions, well, it's a lot of people connecting, a lot of researchers like you and me. So there's a lot of interest in this. Again, I'm thinking forward-looking. So even if there's more of an upfront cost, this is my plug to you again, that upfront cost is worth it. And it's also worth continuing because of employability, thinking about the job market, thinking about even future prospects in academia. And then we're specifically using a group of packages in R called the tidyverse. You do that library tidyverse thing on top of a lot of scripts. One of the reasons we're doing that is that the tidyverse seems to be pretty important within the ecosystem of R packages. So it's another forward-looking thing, getting you facility with another way of doing things in R. So what I'm showing you right here, that central node, these are like connections between tags on these questions. So each of these lines represents a tag, a tidyverse tag. It comes with a per tag, which all these are different packages of R. So each of these clusters represents tags on questions that tend to go together. And you can see, based on the nodes that are at the center, some of the most important packages involved are in the tidyverse. And that's exactly why, sort of forward thinking, trying to think about what will be useful to you in the future. One other comment on this, you can see that there's like tons and tons and tons and tons of different packages. I mean, that's another reason to use it, is use R, is that it gives you access to a lot of different tools. So that's like a little bit of big picture stuff. Why we chose to do R. I'll get to the why teaching the GLM in a little bit. But that's again my pledge to you that the stuff that we're talking about is useful and will show up in other places in your graduate career, or can empower you to seek out resources that might be closed off to other people. So moving on, I want to do again, a broad strokes, high-level overview of the stuff that we covered last semester, and we covered a lot. There was a lot of content in this course. So what I'm going to be hitting on is some sort of common themes that came up throughout the course. Again and again and again, some of the structure that we tried to put the actual content on. Part of the last semester's course was devoted to research methods, more like interpretations of your statistics. This is like what justifies a certain conclusion and how do you know that a certain conclusion is justified. I sort of see three broad topics in the research methods content. One is reliability and validity, one is causal inference, and one is reproducibility. And you can think of these last two as sort of slotting into specific kinds of reliability and validity. I'll talk about that in just a second. On the more statistical side of the course, the more mathy side of the course, we have these three sort of broad level ideas. This idea of models, statistical models, and what they are. This idea of null hypothesis significance testing, and the very specific type of statistical model called the general linear model. And there's sort of a line that separates these two types of content. They do interface with each other. Some of the research methods-y stuff provides some guidance about how to interpret the stuff that you get out of a statistical model. But they're also somewhat separate. You can do the statistics well, but not do the research method stuff well, and not be able to say much about a particular data set. You can do the research method stuff well, but mess up on the statistical stuff. And again, that might mess up what you're able to say from a given study. So both of these are important. Because of how much there was to get through on the statistical side, we focused a little bit more on that. But we did spend a couple weeks on some of the research method stuff, the non-statistical stuff. So let me talk about reliability and validity in a little bit more detail. You can think of these concepts, reliability and validity, as basically they're ways to critique research, to think about research. They're broad conceptual tools that apply in a lot of different ways. Reliability involves the concept of whether you have measures in a particular study that assess anything. So is there something systematic there, or is there not? That's sort of the broad, big picture question that you're asking with reliability. we talked about one way of assessing reliability, but there are several. There are others. That's called Cronbach's alpha. It's a measure of internal consistency. But there are other ways of assessing reliability, like test-retest correlations. There's a statistic called omega. I don't know. There's a lot of different ways of assessing reliability. From a big picture perspective, the question you're asking is a particular measure assessing anything, or is it just noise? The concepts that fall under the validity rubric they're more thinking about like whether certain inferences are justified. That's sort of the way I think about validity. Is a particular inference justified, and for what reasons? So one type of validity that we talked about is construct validity. So where reliability is asking, are you measuring anything? Construct validity is asking, are you measuring anything that you want to measure? So the inference that you're thinking about is it appropriate for me to infer that this thing that I have my participants do is a measure of some concept that I'm interested in, some psychological concept? Does my depression measure, the BDI, assess depression? Construct validity is super important. It's pretty basic kind of validity. If your measures don't assess what you want to measure, then what conclusions can you draw? Probably nothing. The way, the concept that we talked about, the way to assess construct validity is called the multi-trait, multi-method matrix. Basically, you get a bunch of measures that you think should be related to the thing that you're interested in, a bunch of things that you think should not be related to the thing that you're interested in. And you check, is my measure related positively to the things that it should be related to, and is it unrelated to, is there no correlation with the things that it should not be related to? Construct validity is a pretty deep topic, and that was just one method that we covered. There are other ways. The big picture idea is you're asking the question, can I infer from a certain response that someone is genuinely high on depression, for example? And that's the general idea. The second kind of validity is external validity. This is about generalization from one measure or setting or population to another. So you're taking as a given that something is true in this particular, population or whatever, and you want to know, is it reasonable to draw the inference that this is true more generally across other populations? So again, it's another type of inference, but a different one. You're not asking the basic question, is this thing assessing the thing I want it to? You start taking that as a given and saying, does this particular inference also apply to, non-college students or medical professionals or graduate students or whatever the inference in question might happen to be? One of the major ways that you assess construct or external validity is you try to do the generalization. You do a second study that uses other items or a different participant population or whatever. The third type is called conclusion validity. This is a question of whether, based on your specific research design, will you have the ability to draw any conclusion at all? So you're asking the question, is my study informative about whatever? We talked about this in a little bit more detail late in the semester. We have a whole unit on power analysis. That was essentially a more formal way of thinking about conclusion validity. But the basic idea behind ways to increase conclusion validity is you increase your number of observations. That's the easiest, most straightforward way of increasing conclusion validity. You can also decrease measurement error. You can use covariates, but the easiest, most straightforward way is usually you get more observations. And then the last type of validity that we talked about is internal validity. This is about causality. We also had a unit that focused a bit more explicitly on causality. You know, how do you know that you can make causal claims? What assumptions are required to do that? But the most straightforward way is you randomly assign something that you're interested in. And that random assignment ought to eliminate confounders, basically other variables that could serve as alternative explanations for a causal effect. We had readings based on these ideas, but this is sort of from a big picture, you know, a very broad way of thinking about good research design. You think about these different dimensions that underlie research, and these all place limitations or allow you to make specific inferences that you might be interested in making scientifically. Under the idea of causal inference, so this is focusing in on that last type of validity, internal validity. We talked about how you can represent variables that you're interested in, like depression or gender, or a certain program that you're interested in, or a particular treatment if you're a clinical student, as well, basically just words on a page. And you can represent causal relationships that you are assuming that you're hypothesizing, well, assuming are true as arrows. So anywhere that you have an arrow that represents a causal relationship between A and B and C. And anywhere where you don't, you're saying there's no causal relationship whatsoever. It's a pretty simple idea, but it provides you with a good framework for thinking about whether causal relationships may or may not be present. And it also can provide guidance in some ways of what to choose to control for when you're doing a statistical analysis. There are generally three types of sets of causal relationships that you might want to think about if you're drawing one of these causal graphs. They're called directed acyclic graphs. This first one up here is a mediated relationship. So in a mediated relationship, the variable in the center is a mechanism for a causal effect that you're interested in, where a mechanism means that it transmits the effect from A to B. So if it is true that you have a certain drug that acts on a certain neurotransmitter that reduces depression, the neurotransmitter might be thought of as the mediator, the mechanism for the causal effect of the drug on depression. Things that are mechanisms, if you somehow prevent them from operating, so you prevent the neurotransmitter from being activated, for example, that blocks the effects of the drug. So mechanisms are things that transmit the effect, which means that if they can't do that, then the causal effect goes away. The second type of relationship is one way of thinking about confounding, spurious relationships. Something is a confounder if it produces an association that is not a causal one. So one of the examples might be, you might find an association in cities of, the cities where people eat ice cream more also have more crime. Well, a confounder of something that could produce that spurious effect might be heat. So if it's hotter, people eat more ice cream, people also get more irritable and perhaps commit more crimes. But it's not the ice cream that's causing the crime, it's the heat that's causing both crime and ice cream eating. Then this third type of effect, or type of set of relationships, is called a collider. A collider is something that's caused by two other things, but it itself does not cause either of these things on the sides. Colliders are important to understand because if you control for these things, you can produce relationships that are not causal. So this is a way that controlling for something might not help. And one way of thinking about this is you might find among college students that IQ or intelligence, it has a negative relationship with conscientiousness. You might think, well, that doesn't make sense because, like, if you're conscientious, why would that cause lower intelligence? But what might be happening is that being in college is a collider for both conscientiousness and intelligence. One reason that you can get into college is that you're intelligent. One reason that you can get into college is that you're conscientious. The people who are neither conscientious nor intelligent don't get in. That's what causes the negative relationship. And if you want a refresher on that general idea, there's a great paper by Yulia Rohrer from last semester that sort of goes through different examples of these colliders. So when you're thinking about causal inference, generally you want to control for confounders, but you don't want to control for colliders or mediators unless there's like a special procedure for assessing mediation. But that's the general idea behind causal inference: control for confounders, don't control for colliders, and you never know exactly what's true. You just assume it to be true, and then given the assumptions, there are different ways of identifying causal effects. The last sort of big picture research design idea is reproducibility. This is a little bit different from the other two in that it focuses more on how the sausage is made, so how science gets done. And the general idea behind reproducibility is that there are certain scientific processes that are more likely to lead to things that are true, and there are certain scientific processes that are less likely to. And you want to design your research process, your way of acquiring data, in such a way to maximize reproducibility. To be concrete about this, this is like a schematic way of thinking about the research cycle. So first you generate a hypothesis, design a study to test it, you conduct a study and collect data, analyze the data, and test the hypothesis statistically, interpret the results, and then go on to communicating and publishing it. And the cycle begins anew. Unfortunately, things aren't always quite as simple, and there are lots of things that can go wrong with this process that can lead the results to not be true or not fairly represent reality. And there's growing evidence that this is actually true. It's not just a hypothetical, that it's true for psychology and for a lot of other sciences too. There's a whole field called metascience that's dedicated to studying this. So it happens to be one of my primary interests, which is part of the reason I emphasize it quite a bit in class. Sort of a new field that's sort of trying to tackle these issues. But anyway, these are different things that can go wrong with the research process. So there's one that we talked about in a bit of detail called p-hacking. Basically, it can be hard to know once you have the data what the right way to analyze it is. Do you exclude this person because they're an outlier? Do you keep them in because they might actually reflect something interesting about their phenomenon? Do you include a covariate? Do you not? Do you transform your variable by doing a log transform? There was a whole exercise that I had to do dedicated to this idea. It can be really, really hard to know exactly how to interpret your data. And that leads to slight differences in the results, and it can be easy to persuade yourself that the ones that produce results that you like are the ones where you made the right decisions. Unfortunately, that can lead to results that are not reproducible if you do the study again. you won't get exactly the same results, even if you're making all those decisions in exactly the same way. That's what you have. Another major one is hypothesizing after the results are known. The way I like to think about this is if you're throwing darts, let's say that this is the dart. Hypothesizing after the results are known is a little bit like seeing the dart and then drawing a bullseye around it. So you're saying, like, after you saw the results, oh yeah, that's exactly what I would expect. But if I asked you to throw that dart at a dartboard or make the predictions before you'd seen any data, you might be making entirely different predictions. This is another way that you can fool yourself and end up with the results or interpretations that aren't true. There are a bunch of others. This is just some of them. What's more important even than knowing the specific threats is, oh yeah, we also talked about one towards the end of the course called overfitting, which is making an overly complex model that too much for the data that you have. So yeah, what's more important than knowing the specific threats is knowing what to do. One is using the right inferential tool for the job. We went through a lot last semester. One in particular that is a little bit less common in psychology is called equivalence tests. That's a way to say that the data result is too small to care about, which is hard to do using the statistics that a lot of people have in the last couple decades. Another important one is documenting and sharing both your materials and data. And then perhaps the best one, the one that fixes a lot of problems, is known as pre-registration. That's basically committing to what decisions you're going to make to analyze a certain set of data ahead of time. And of course, there's a website called the Open Science Framework that helps you do all this. So if you all are thinking about, let's say you're designing your master's thesis, I urge you to think about these things and go ahead and do them. Go to OSF, there are templates, there's lots of help files, there's lots of help increasing all the time. Talk to me. I've been pre-registering all of my studies since I started thinking about this because I think this is important. I'm perfectly willing to provide you with guidance if that would be helpful. I've been going pretty fast, so let me just pause. Are there any questions about this research methodsy side of things? Is this pretty familiar? Yeah. Did you have a question? Is this pretty familiar for you all ready to go? Good. So that's the research methodsy side of things. This semester, there's the option to go more into research methods. I've designed in some flex time that we can either use to go into certain topics in a little bit more detail or hit some additional topics. And stuff related to research methods are one of the options. As the course is structured right now, there's a bit more emphasis on the statistical side of things, but we certainly can go more into the research method side of things as well. On the statistical side, the place that we started with last semester is this idea of statistical models. A model is, as I presented it, is a way of making a prediction. You take some input and you predict an output. You can compare your predictions to the things that you actually observe and see how wrong you are. You can either be really wrong or you can be not very wrong. There are lots of different there's lots of terminology for naming these different parts of a statistical model. The model part of it is often called explained variance, whereas the degree to which you're wrong is often called unexplained variance. You also get into this terminology of having outcome variable, predictor variables, and these things that you modify the predictor variables with called parameters, or I also use the term coefficients. And the degree to which you're wrong is often called residuals. But they're all relying on this idea that you can create some sort of mechanism for making predictions about the world. You can compare your predictions to reality, and that gives you a sense of how wrong you are. There are different ways of measuring wrongness, but one common one is, let's say that you're making the same prediction for everybody. The prediction is 0. One common way of measuring how wrong you are is you just take each observation, you subtract your predictions from that observation. That gives you a prediction error or a residual. You do this a bunch of times. So you do this for each observation in your data set. It's often the case that we square them and then sum them. When I introduced this idea, I also talked about how there are alternative ways of measuring how wrong you are. But the one, of course, that we focused on most last semester was squaring them and summing them. And then the sum is called the sum of the squared errors. SSE, this is a measure of how wrong a given model is. And of course, if you can do this for any model that you have. If you allow your model to sort of have some contact with the data, if you search through a bunch of different models, you can often find one that, or you will always find one, that is best. Best in the sense that it produces a minimum value for the sum of squared errors. It is least wrong. So that contact with the data that your model has, that's called a parameter. A parameter estimate is, at least in the general linear model, is one that minimizes the sum of the squared errors. Once you have a couple sum of squared errors, you have a couple models that, and you've measured how wrong they are, you can do this procedure called null hypothesis significance testing to compare models to see, is this model less wrong than this one? And is it less wrong to a degree that I should care about, where I should make the decision that this particular model is better enough to trust than this other model, that it's probably true. It's probably closer to reality. So the way this often goes is you're often working from sort of a pretty general model, the general linear model. And based on that general linear model, you define what are often called the compact and the augmented model, or sometimes the null model versus the alternative. In the Compact model, what you're doing is you're fixing a part of the model. You're not allowing it to have contact with the data. You're assuming that a particular parameter takes on some value. So often what you're assuming is that a particular parameter value, one of these b's, one of the coefficients, is 0. It doesn't have to be 0, but often it is. And what you compare that to is a model where you allow that parameter to be estimated. You allow it to have contact with the data. You find the value of that parameter that minimizes the sum of the squared errors. So that gives you a difference in how wrong these two models are. This is a comparison of models. And usually, as I mentioned earlier, your null model is a simpler version of your alternative model. So you can think of this process of null hypothesis significance testing as allowing your model to be a little bit more complex. And you're asking the question, is that extra complexity worth it? Is it worth it to estimate this one parameter, where the parameter estimate might represent a particular question that you're interested in, like, is some treatment effective? Once you have those compact and augmented models, or the null model and the alternative model, you compare them using some sort of statistical procedure. The two major ones that we talked about last semester are F and T, where F is T squared. So there's a direct relationship between these two things, although you can do a few things with F that you can't do with T. So with F, you can test joint hypotheses where you assume that, say, two things are equal to 0 at the same time. T doesn't allow you to do that. And then if the statistic that you've calculated is sufficiently large, you choose to reject the null hypothesis, otherwise you retain it. And usually the way that you do this is you calculate a p-value and compare it to alpha. And what's kind of amazing about this whole procedure is how it applies very straightforwardly to a ton of different situations. There was never a time that we strayed from the null hypothesis significance testing framework last semester. And that's kind of amazing that it's able to accommodate so many different situations. What was also cool about this whole framework was that last semester, there was also never a time that we strayed from the general linear model. So this process of choosing a model to start with and defining the null and alternative hypotheses, every time we were working with null and alternative hypotheses, we were working with two different variations of the general linear model. One where we assumed some parameter was fixed, and another where we allowed that parameter to be estimated from the data. What the general linear model is basically adding a bunch of stuff up. So you take one quantity, add it to another, add it to another, add it to another, and all we did when we introduced other more complex versions of this general linear model was we added another quantity. That's the only thing that we did. There are a couple of assumptions that underlie the general linear model. We talked a bit about what those assumptions are. One is that all these x's that appear in the general linear model are measured without error. There are ways to relax each of these assumptions. And just to forecast where we're going to go, one of the options, well, we're going to talk about one specific way to relax one of these assumptions. One of the options for a topic that we could cover is talk about how to relax another of these assumptions. So basically, where there are extensions to the general linear model, often involves making one of these assumptions less strict. The second is that each of these prediction errors is independent of each other. So knowing about one observations error tells me nothing about some other observations error. This is one of the assumptions that we're going to relax this semester. We'll talk about what to do when you do have dependent measurement error. But in the strict unmodified version of the general linear model, this is a pretty important assumption. When this one is violated, you've got big problems. Another one that's not quite as important, but we did talk about, is that the prediction errors form a bell curve. They look like that. You've got a couple extreme ones. Most of them are concentrated towards the middle. Another one is that the prediction errors have what's called constant variance, or there's this fancy word that's kind of funny, homoscedasticity. What this means is that if you're somewhere on one of your predictors, so you're looking at people who are a 9 on depression, the variance in the residuals for people who are a 9 on depression is the same as it is for people who are a 1 on depression. That's what that means. Then the last one is that there's a linear relationship between the predictors and the outcome. So if you move from a 1 to a 2 on depression, that produces the same predicted increase in anxiety as going from a 2 to a 3. And we talked about different ways to relax each of these 3 last assumptions in the general linear model. So one is transformations, another is including product terms, x squared terms. We'll talk a little bit more about how to relax both this assumption. I'm going to provide you with another method of relaxing this assumption, and especially assumption 2, the assumption of independent errors. But these are basically what makes the general linear model work. As I've already said, what's amazing about the general linear model is how many situations it can apply pretty well to. It does a pretty good job in a lot of different circumstances. So here are all the situations that we covered last semester. And this is, I mentioned earlier in the lecture, I'm not going to come back to that idea of covering a lot of material. Here's some evidence. So we learned how to handle each of these cases. What's confusing in some ways of teaching this course is all the different terminology that shows up on the right side. So ANCOVA, two-way ANOVA, multiple regression, polynomial regression. And this ties back to another choice that we made in designing this course. One of those choices was to emphasize what's common about all these different special cases. Even though they're called different things, sometimes they have a different history of development, they all can be understood as variations of the general linear model, where you're just adding a bunch of terms up and getting a prediction, and then seeing how different your prediction is from reality. And that's pretty amazing. So I hope you can appreciate a little bit, how much ground we covered last semester. And, from my perspective, you all demonstrated a lot more understanding as the course went on. You know, I saw continuous growth. I don't know if you all are able to appreciate that. Maybe if you go to a conference or a workshop or something, you'll be able to appreciate that more by seeing, you know, alternative ways of teaching this course and how you might understand things had the course been structured differently. I don't know. That was my experience when I was a graduate student. It was tough to go through the course, but then, you know, given a little bit of distance, I started to appreciate, you know, the gains that the long-term gains from structuring the course in this way. So that was the content from last semester. A lot of stuff. This semester did move fast, but there were also some common themes. We always worked from that perspective of making model comparisons or estimating parameters and seeing whether it was worth it to estimate that parameter from the data. And a lot of the method stuff tied back to this idea of reliability and validity. What we're going to start with this semester is we're going to finish up some content related to the general linear model. So one case that we did not get to last semester was how to deal with categorical variables. So if you're looking at ethnic identity, Asian versus Black versus whites. So how to analyze data sets that involve those multiple category variables. One of the reasons I delayed this unit to this semester is that there are a bunch of different ways of analyzing these categorical variables. And I'm going to especially emphasize one approach that involves what's called planned orthogonal contrasts. But you will see other methods of analyzing categorical variables out there in papers that you read. I'm also going to go through some of those other approaches and try to give you some sense of, you know, when to use the different approaches that we go through. The planned orthogonal contrast is the one that I most prefer, but it can't do everything. It's really good in situations where you're making specific predictions ahead of time and testing those predictions. It's less appropriate for situations where you don't know what specific comparisons you want to make. So the other two approaches that I'll go through are something called dummy coding, and then a completely exploratory approach where you have multiple comparisons. And I'll talk about this idea of adjusting for multiple comparisons. The multiple comparisons idea is going to tie back to this, you know, research methods, p-hacking kind of content. Perfectly legitimate to do multiple comparisons, but you need to take some extra steps if that's truly what it is that you're doing. Or at least that's the argument that I'll make. So again, I want to emphasize ahead of time, I don't think that there's a whole lot of consensus about how to handle these variables that involve multiple categories. So I don't pretend that, you know, I'm the authority on this. I do have opinions, and I'll talk to you about why I have them, but you will see a lot of different approaches out there in papers that you read. Later in the course, we'll move on to some content that is not covered by the standard general linear model. So that first topic, I think we'll spend maybe the first 2 to 3 weeks on it. That's part of the standard general linear model. We'll still be working with the same statistical model that we have all along. These latter two topics are going to be extensions of the general linear model. So one of the reasons that this course is structured the way it is that there are a lot of extensions that cover special cases that are pretty easy to understand if you have a good grounding in the general linear model. And I'm hoping that you'll be able to see why that is once we move to these extensions. This first extension that I think we'll cover right after the categorical variables unit involves situations where you have an outcome that is a dichotomy. So yes versus no, respond versus not, error versus correct response. So we're going to be talking about situations where that's your outcome variable. And it turns out that there's a nice framework for handling that special case that belongs to an extension called the generalized linear model. A little bit weird why it's called generalized, and we have the general linear model. I don't know why that is. And that's just what it's called. It's also called logistic regression. If we have time, I might get to another extension of the generalized linear model where you're working with count outcomes. So you're measuring the number of people who, got sick within a given city. Turns out there's a nice way of handling those count outcomes. That's a little bit more preferable to the general linear model in some cases. So the generalized linear model can handle a lot of unusual types of outcome variables. That's what it's developed for. So we'll talk about one application of that, and if there's time, we'll talk about another application as well. The second major topic that I think is really important and we'll spend quite a bit of time on, it's going to be at least a month, probably 2 months, so a big chunk of the class. And that's handling this case where you have errors or prediction errors that are dependent on each other. Common case in psychology for why that might be true is you have the same participants who are measured multiple times. If you know someone's prediction error at time 1, you'll probably also have a sense of what their prediction error is going to be at time 2. If the model underestimated what their response was at time 1, you'll probably have to do that at time 2. There's one way of handling this that does fall within the standard general linear model that involves taking specific types of difference scores. So we'll spend some time on that, if only so that you can understand what you might do reading in other papers. And there are some cases where this is perfectly adequate for analyzing your data. But there's another framework this is another extension to the standard general linear model that's often called the linear mixed effects model, or sometimes it's called a hierarchical linear model. These models are really great for handling cases where your prediction errors are dependent on each other, to have some sort of structure to them. And it turns out that they're extremely flexible, and that's why I want you to know about them, because I'm seeing this approach more and more in papers that I read, and I'm using it more and more in research that I do. So I think this is a super flexible tool if you're doing any sort of cognitive tasks, if you're working with students within classrooms or patients within clinics, you're probably going to need this kind of model. What's also nice about it is that if you have multiple sources of dependency, so if you have the same stimuli, let's say that you have a list of words that you have to respond to, and everybody responds to those same stimuli. That's one thing that might produce an error structure that has some dependencies. Because if someone responds slowly on that one stimuli, another person will also probably respond slowly as well. Well, in order to analyze that kind of data appropriately, where you have people responding to the same set of items, you need a linear mixed effects model. So we'll spend a lot of time on that. Super useful extension. Like I said, I see this all the time. It's also, it can be a little bit tricky to understand what's going on with linear mixed effects models. So that's another reason why I want to take some time with them. And then finally, we have some flex time. So another benefit, I think, of taking the structuring the course the way we did is that we have actually quite a bit of time to talk about special topics that might be relevant for research that you're doing. So I've intentionally built in some flex time that we can use for special topics. I've listed some special topics here. Some of these I have ready-made lectures for, some I don't, but are just interesting and might be interesting to you. I'm also completely willing to take suggestions. So one of the things that I'll do, just like I did last semester, is in the first set of structured feedback I get, I'll be asking you for topics that you think might be useful. And I'm totally willing to cover one of those topics if there's a lot of demand for it. But things that have come up in my own data, I've done quite a bit of longitudinal work, so I get missing data problems all the time. I have a ready-made lecture for how to, that talks about how to deal with missing data. I also have quite a bit of experience with meta-analysis. It's part of my interest in meta-science, or the way science gets done. I see that a lot. Meta-analyses are pretty tricky to interpret if you're just reading the paper, because it's hard to know, like, okay, what should I be focusing on? How do I know if this meta-analysis is good? I'd be totally happy to talk about that. I've taught a class on meta-analysis my first semester here, and it's a pretty rich and interesting topic. These two issues, exploratory and confirmatory factor analysis. Confirmatory factor analysis is one way of relaxing that assumption of no measurement error in predictors. This allows you to incorporate measurement error in predictors. It's part of this family of methods called structural equation modeling. SEM is pretty complicated, but pretty useful, I think. There's no way I'd be able to go through everything that you can do with SEM because it's a lot. But I'd be totally happy to provide an introduction, maybe talk at least a little bit about the issue of measurement error and how to assess whether your measures are good. Because that's essentially what this allows you to do. So that's going to be the course. We're going to go through quite a few topics yet again, but I'm highly confident that we can get through them because I was pretty generous with my scheduling, and yet we still have extra flex time. So I'm hoping that this semester can be a little bit less frantic than the last one because we've spent so much time on different variations of common themes. So this is where I hope you'll see some of the benefits of the structure that we took last semester. Thanks a lot, everybody. And I'll get back to you about scheduling for the drill section. And otherwise, I'll see you on Wednesday.